Very good. So it's up to you. Oh, sorry. So we have Lynge Lauritsen telling us about Superresolving Herschel imaging, a proof of concept using deep neural networks. And you have 12 minutes. I'll warn you at 3 and 1.
Thank you. Yeah, hello. My name is Lynge Lauritsen, and I'm here to present the work that my collaborators and I did trying to use convolutional neural networks to superresolve the Herschel SPIRE images, trying to get the similar, how do I change? There we go. Similar image characteristics to those found in JCMT SCUBA-2 450 micrometer images. The reason we want to do this is really twofold. It partly comes down to sky coverage and partly comes down to image characteristics. If we look at the image there in the right, the background image is the Herschel SPIRE 500 micron coverage of the cosmos field, while the gray square overpainted in the middle is roughly the area covered by the JCMT SCUBA-2 studies survey of the same field at 450 micrometers. If we then look at the table in the bottom and the image characteristics of the JCMT SCUBA-2 450 micrometer images compared to the Herschel SPIRE 250, 350, and 500 micrometer images, we find that when comparing JCMT against, in particular, the closest equivalent Herschel SPIRE band, the 500 micrometer band, that JCMT have a much improved point-weight function full width half maximum and a much improved confusion noise. So the idea really came down to, could we use the old Herschel SPIRE data to try to superresolve it so we could get some of the image characteristics of JCMT and maybe we could gain some additional knowledge doing that. So the way we decided to go around trying to do this was we decided to use an autoencoder in a UNet configuration. The architecture for our autoencoder was inspired by the Galaxy GAN generator, but we do have some quite significant differences in how we are using it in this case. The schematic of the autoencoder we used are shown here in the bottom, and I want to draw your attention towards the final activation layer in which we use a sigmoid activation function. I'll get back to later why this is important to us. Due to the lack of sky coverage in the cosmos field of the JCMT SCUBA-2 data, we had to use both a combination of simulated and real data when training every epoch. So the way we went about doing this is really also where we start differing quite significantly from the Galaxy GAN, which inspired our autoencoder. Because we're not using a GAN, we don't use a discriminator to train our network. We feel that what we're interested in this network is the source positions and the source fluxes, and we feel we can define this in a loss function quite sufficiently ourselves. So what we have is a custom loss function where we use a standard L1 loss, and then we use a series of image characteristics that we achieve using phototils on the images during the training. So what we use is we have the mean flux difference between the target image and our generated image in order to try to get the integrated flux in the images right. And then we use the median flux difference in order to try to get the background level of the flux in the images right. And then we use an aperture flux difference where we identify where there are sources in our target simulated data, and then we cross-match these locations onto our generated data, and then we find the flux differences inside an aperture photometry from there in order to train our loss function so that it should hopefully encourage the network quite significantly that the things we are interested in are the very locations where we have sources, so it should recreate the source positions and the source fluxes. When we then train on the real data afterwards, we do the exact same thing all over again, but this time we add in an additional step. We also identify sources in our generated data and cross-match those locations onto our real target data. And by doing this, we hope to punish the network if it should start inventing sources that doesn't exist. If it invents a source that doesn't exist, it should hopefully be identified as a source in the generated data, but as there's no signal there in the target data, that should hopefully teach the network not to do that. Of course, that's well and good, but the important thing is whether or not it works. What we see here is the output from our network. On the top of the image, we have our generated data and our target data, and in the bottom, we have these 3 Herschel SPIRE bands that we use as input. you will probably immediately have noticed that our noise characteristics of our target data, our generated data, are massively different from our target data, and that's by design. As I said before, we use a sigmoid activation layer in the final layer of our network. And what that does is it prevents the network from predicting any negative values. As the JCMT data's noise fluctuates around 0, we efficiently can't recreate the noise, and that's because we're not really interested in noise. We're interested in source positions and source locations, not all the rest of the image. When we then look at our generated data and try to look at some of the sources that we can see in the generated data and then look at the same positions in the input data, then we can often find the sources that we find in the generated data. We can often see sources at those positions in the higher resolution Herschel SPIRE bands, the 250 micrometer band and partially in the 350 micrometer band. But when we then look a bit closer at those positions in the Herschel SPIRE 500 micrometer band, we find that the relative fluxes in our generated data matches the relative fluxes in the Herschel SPIRE 500 micrometer bands, which of course makes sense because that is the closest band in terms of wavelength to what we're trying to achieve. So it seems like our network takes all the information from the range of different Herschel SPIRE bands and combines it into generating the closest equivalent to the JCMT image that it can inside the loss function that we have specified for it. As I said, we are interested in some of the image characteristics of the JCMT data, amongst them, of course, the point spread function. When we do a stack of the matched sources and then do a cross-section to get the point spread functions, we find that the point spread functions of our generated data in terms of full width half maximum and shape are very comparable to that of the JCMT SCUBA-2 450 micrometer data. But it's, of course, significantly smoother, probably in large part due to the fact that we have removed noise from the images. But as I said, what we really want to do and what we designed our loss function to do was source positions and source fluxes. And when we look at the source positions, we can see the angular offset on the y-axis between where we expect the source to be based upon our generated data and where we find a source in the target data. And generally speaking, we generate our sources inside 10 to 12 arc seconds of where real sources exist, and almost all the sources are generated inside a radius of about half the full width half maximum of the Herschel SPIRE 500 micrometer data. The next part, of course, is the source fluxes. And when we then look at how we do that, we find that when we have, in this plot, we have the target aperture flux on the x-axis and the superresolved aperture flux on the y-axis. We find that we, inside some scatter, of course, has roughly one-to-one correlation between this flux that we predict and the flux that we would hope to predict based upon the target aperture fluxes, down to a target aperture flux of about 9 millianskis. At sources fainter than 9 millianskis, we seem to continuously over-predict the source flux. But that is still a significant improvement when we compare that to what the 3 sigma confusion noise for the Herschel SPIRE 500 micrometer data is, which is around 20.4 millianskis. When we also look at our completeness and our purity, we find that we have a very high completeness of 95% or better, down to about 15 millianskis, as well as very high purity, down to about that level as well. Below 15 millianskis, our completeness drops very significantly, but the positive side of that is that our purity remains high, even when we underpredict the number of sources we should find at fainter fluxes and overpredict the flux of those sources. We do generally tend to be fairly confident that if we predict there to be a source, there probably should be a source in that location, or close to it. And going forward, what we intend to do is we intend to try to super resolve all the Herschel SPIRE data from the Cosmos field and make a source catalog. And it is also our intention to do the same thing on the fields used by the JCMT SCUBA-2 radius project. And the final point that we are actually working on right now is we're trying to work on cross-correlating the sources we predict against our surveys as a way of seeing, what sources do we predict that are observed elsewhere as well. And yeah, if you want to know more later, then yeah, talk to me or contact me, and I'll be happy to respond. And thank you for listening.
Thanks a lot. So we have time for a few questions. We have one here, and then here.
Hi, Soteria Fotopoulou. If I didn't miss something here, you used the 250 as input in your training, right? The 250 microns.
We used all three Herschel SPIRE bands.
You used all three Herschel bands. So I wonder, how does your result change according to the slope of each source in the SPIRE bands? For example, would you have a different performance when it comes to AGN and star-forming galaxies?
We probably would have a slightly different performance. We haven't gone into that much. Generally speaking, I think the network should perform fine as long as the source itself is present in 250 or 350, because it does seem that it finds a lot of the positions from there. But how exactly that would work, I don't know. I would have to do more, go more in depth with that, and we haven't done that yet.
Okay. Another question here.
Yeah, it's Henry. So can you just explain to us what the scientific applications are of your super resolved images? Because it's hard, looking at your talk, to think about ways in which to test that scientific application. You didn't actually, maybe you did right at the start and I might have been asleep. What's the scientific application of your super resolved images?
Well, the scientific application is that a lot of places where we have Herschel SPIRE data at relatively poor resolution compared to JCMT, it would become interesting to try to see if we could predict source fluxes of some of the sources that might be more difficult to find in the Herschel SPIRE 500 micrometer bands, but we could super resolve here, and then we could compare those, do a color comparison against sources identified in other surveys from that.
Okay, thanks.
Any other questions? If no, let's thank Lynge again.